Welcome to the CAD for Assurance webinar. So since the start of this webinar, I think we have 3 great panels, 1 course demo, and this is the 6th tool demo. And today we are very happy to have Professor Aysu and his students, Seetal, to introduce the scan train locking. And we also have the second talk from Professor Hoque from University of Kansas. I will introduce him later to avoid further delay. So Seetal and Aydin, please go ahead. So.
Thanks very much, Aydin, for inviting us to give this talk. And we are very happy to share our latest work with you. So what we are going to do today is we have a cool demo prepared by Dr. Seetal Potluri, who is a postdoc working with me for the last 2.5 years. So he will give the cool demo, and I'll just briefly go through some of the basic concepts here with a few slides. But he will be doing the main job because he is the real brain behind this operation. So this work is SeqL, scan chain locking, along with a broad security evaluation. We are from North Carolina State University, but we also acknowledge Akash Kumar from Technical University of Dresden for enabling this work. Next slide, please. So what we are going to do today is to describe our SeqL here. Essentially, the idea is to have an input netlist that can be entered to our flow. This input netlist is secured with SeqL, and as a result, we will get an obfuscated hardware design. Our goal is to use this obfuscated hardware design to protect against hardware IP theft that can occur either from untrusted foundries or by reverse engineering. Then the tool runs several different attacks automatically, such as the set attacks, SMT and fall, and there are other attacks that have been proposed against logic locking. The tool also will use an unlock design, which is called the Oracle design. This is optional, so some attacks will not use Oracle, but most attacks do. And finally, the tool that we created will tell us if the resulting locked circuit is either secure or insecure. Okay, so that's the high-level idea. Next slide, please. So, by the way, let me know if you have any questions. Please interrupt and ask or type it into chat. So here is the common threat model for logic locking. So again, we are trying to protect hardware IPs because these are valuable IPs and assets that we spent millions of dollars and many engineer hours. So the circuit that we created will be locked at the gate level, and then it will be synthesized so that this can be outsourced to any fabrication facility, whether we trust them or not trust them. The attack will look at an activated IC, which is what we call an oracle. The attacker can either do reverse engineering, or the attacker can be the fabrication facility. So the attacker, we assume, that knows the details of the hardware design. Yet the logic locking aims securing the design by obfuscating the input-output behavior. So if you don't know the input-output behavior, unless you know the secret key that is used in the logic locking, then you cannot reverse engineer the hardware details and generate a functional design. So here is the logic locking in a nutshell. So we have a circuit. The circuit will be transformed by adding some new logical gates, extra logical gates, that will have zero effect on the functionality if the secret keys are applied into the circuit. Right, so there are many different logic gates that you can use, typically XORs, XNORs, and so on. But if you don't know these keys or the key inputs, then the circuit will function then the circuit will function incorrectly. However, one thing to note here is that this encryption, so-called encryption, is not done by cryptographers. This is done by hardware design engineers. And moreover, the costs are very constraining here. So we can only add a few logical gates and try to get an obfuscated result, right? So if you consider the cryptographic circuits like AES, it uses complex nonlinear functions and many round of operations, right? So we don't have it here. That is why there is an inherent vulnerability of, I would argue, any given logic locking scheme. So that's why there are some attacks that can actually try to break these systems. The attacks work by estimating which keys are functionally equivalent. And to do that, the logic gates are formulated as Boolean clauses. So I'm not going to go into the details of this, but the idea is to represent a logical gate as a set of logical clauses that uses the inputs and outputs. So you can do this on both the regular gates and as well as the logic locked gates, and formulate the function, the full function of a given locked circuit. Next slide, please. And the attack essentially will use these CNF, the cumulative normal form, will use this CNF and will generate two versions of the circuit, right? These two versions here shown in the second, in the middle. So these two versions will then pass through a formal equivalence checker. And the idea is to evaluate all possible inputs and outputs formally of these two versions of the circuit, such that you can efficiently brute force the secret keys, right? So as I mentioned, so the secret keys are not unique. There are groups of different keys that achieves the exact same functionality. So the idea is to efficiently group them together and to brute force these, what we call key equivalence groups, right? So, and if we do that efficiently, so if there are not so many groups, then we can simply brute force them and figure out which key actually is the correct one. And we do that by using these CNF formulations with formal equivalence checkers and the responses we obtained from the activated oracle. So that's the highlight in a nutshell. So Seetal will now describe very quickly the idea behind SeqL, and then we'll give you a quick demo.
Thanks, Aydin. So as Aydin explained, we are actually doing a scan locking scheme in this work, and also broad security evaluation. So we have gone into great depth about satisfiability-based attack because the attack is well known, very powerful, and also the source code is publicly available and is stable. So, but the attack generally is generic in our evaluation platform. So, but we use this as a case study to explain in detail. So as Aydin explained, this is the satisfiability-based attack. So, which tries to find the distinguishing inputs and then prunes of the equivalence classes, and then we can show this on an example circuit. Now, this is well known. So recently there has also been work on sequential circuits. So essentially, if you would like to launch a satisfiability-based attack on a sequential circuit, it is straightforward to do that through scan chains. So there has also been work that tries to secure scan chains because of the resulting vulnerability. So we show this figure actually to demonstrate real-world sequential circuits. Let's assume we are trying to secure this IP, and this IP is accessible through RI and RO registers, where RI is the input register which controls the IP, and RO is the output register which observes the IP. So scan input and scan output is pretty much used to apply the stimuli and to capture the responses. So what we propose is SeqL, which is a secure scan locking scheme. So in practice, to secure sequential circuits, there are a lot of techniques available in the literature, but we focus on scan locking in particular because there are deficiencies for those schemes proposed in the past. So we found out there is a technique called EFF, which is insecure to SAT-based attack. So we propose this technique called SeqL, which actually secures the scan chains. It's a really cool technique. So I'll go into the details of how this works. So let's assume you have a sequential circuit with 4 flip-flops. And I'm not going into the details of the implementation of the combinational logic. Let's assume there are 2 qubits for the combinational logic and you have 4 flip-flops. And let's assume 2 of the flip-flops have feedback and 2 of the flip-flops do not have feedback. So the basic idea of SeqL is actually to lock these flip-flops without feedback, because if you lock flip-flops with feedback, it is well known that you can still launch the SAT attack in multi-cycle attack. So in order to avoid that, we only lock flip-flops without feedback, because these do not appear during the timestamps in a multi-cycle attack during the unroll. And also the additional component of SeqL is that we add some additional XOR gates at the input of flip-flops. So most of the scan locking techniques actually try to add an XOR gate at the output. So we split the output of the flip-flop into 2 outputs, the regular output and the scan output. And then also we lock the input of the flip-flop as well as the scan output. So this is the very high level overview of SeqL. SeqL is very simple in terms of implementation, but very effective in practice. So when you launch a SAT attack on this, what we observe is that first you need to unroll the sequential circuit into combinational circuit. So you have XOR chains which are obtained when you unroll, then you launch the SAT-based attack through the scan chain. So it is very important that when you have a sequential circuit, the attack is always launched through scan chain. So that's why we're trying to secure the scan chains. So when you do that, this is the kind of key that is obtained. Without loss of generalization, we have assumed an all-zero key. It is possible to have any possible key, but we do an all-zero key because for the purpose of experiments, if the solver returns the all-zero key, it means it is insecure, and if it is returning not an all-zero key, it means it is secure, at least in terms of the combinational part. That's why we demonstrate here the functional portion of the decrypted key, which is the combinational part. So CK0, CK1 and FIK0, FIK1 are the key bits, which is the portion of the key, which is the combinational part. So since it's not all zero, which means we are able to successfully secure the circuit. That means if you run a SAT attack, it is not going to give you a correct key, which means the circuit will not function correctly if you launch the attack and use that key. So how does SeqL work? So essentially SeqL works in a way where you're trying to hide the key and also try to isolate the key from the functional operation. So if you try to understand SeqL, we can represent the keys using a key assignment graph, KAG, where the root node is a dummy node and the first level is the end of the scan chain. So we have seen in the previous slide that last key bit will be SQK1. So that will be the beginning level in the key assignment graph, and then you keep on going away from the scan chain until you reach the first lock. So what we represent here is a couple of bits. The bit that is used to log the output of the flip-flop, scan output, and also the input of the flip-flop. So the pair is what is represented here, and different possibilities are represented. So we have, in practice, there are 4 combinations possible, but we are only showing certain combinations because this graph actually tries to obtain those key combinations which ensure the scan correctness, because when you're trying to launch the attack through the scan chain, it is only possible to achieve SAT-based keys only in the scan correct mode. So only those key bits which return scan correct output will be returned here, but not all of them are functionally correct. As you can see in this table, we try to show 4 combinations. Exactly, there are 16 combinations, but we only show the portion in order to ensure we are able to capture the key insights in the table. So the first case, it is scan correct, which means if you run the SAT attack, it is going to return that key. And it is also functionally correct, which means if you apply that key, the circuit is going to function correctly, which means it's not secure. In the second case, it is functionally correct, but you cannot launch a SAT attack on that. That means you don't get this key when you run the SAT attack in the scan mode, which means the SeqL is able to hide a key, which is an important property of SeqL. And then there is one case where it is neither scan correct nor functionally correct, so you don't get this key anyway. And the last case is the most interesting case actually. So this is returned when you run the SAT attack through scan chains, but it's not functionally correct. So this is the main property that SeqL tries to exploit, which is not there in any of the prior attacks. So what is the key assignment graph? You have a vertex set and you have an edge set. So an important property that we prove in the paper, I'm not going to the details here, is that the parity of both left and right edges of a vertex in the KAG are identical. So there are different key bits that we have seen. So at each level, you have a scan bit as well as an inversion bit. So as Aydin explained, when you're trying to do logic locking, it's also possible to introduce another inverter. So that is INV. If there is an inverter, then INV bit will be 0, 1, otherwise it will be a 0. And SQ is the scan bit and FI is the input bit. So this is the flip-flop where you're trying to look at depth I, and these are all the flip-flops from there till the end of the scan chain. So that's what I represent here. And the basic idea of SeqL. So in this presentation, I'm only going to go into the automation. I'm not going to go all the details of SeqL because this is supposed to be a demo presentation. So SeqL, what does it do? So if you lock M scan flip-flop without feedback, then the odds against the functionally correct key is 1 minus 1 by 2 power m, which means as you increase the number of flip-flops, the probability that it will return a wrong key is very high, which means the security level actually increases. That's the main concept which we are trying to exploit. So this is how SeqL is done. So earlier we have done a semi-automation flow, which we have put on GitHub as part of the CAD for Assurance website, but we try to automate and make it scalable to very large benchmarks. So the way the SeqL automates is that it has multiple steps in the automation. You first lock the scan chains, then run unroll to form a combination logic, and then you run the SAT solver. It could be any attack, but we have used a SAT attack to begin with, and then you give the oracle. And the question might come that for the we'll see that later. So then you do that and you get the sequential key. And the important part is that, as we have seen, the combinational key is the most important part. If that is not all 0, then we're good. So we extract the combinational part and then check if it is formally equivalent. So the formal equivalence part is very interesting. So in general, an attacker is unable to check if it is formally equivalent because he does not have access to the golden original netlist. He only has access to the locked netlist. But in our case, because we are looking at a designer point of view who is trying to secure his design, he does have access to the original golden netlist, so he can do formal equivalence checking. So SeqL actually tries to lock, and then due to the inverse exponential dependence, as we have seen in the previous slide, the method actually scales very well to very large scale industrial IPs because you're trying to linearly increase the area overhead, but you're trying to get an exponential increase in security. So what are the different steps in the automation? The first step is actually to lock the flip-flops by inserting those 2 key gates for each flip-flop, and then scan and roll to form those huge XOR chains, run the attack and decrypt the key, extract the combinational portion and the combinational portion of the circuit itself in order to run the check, the formal equivalence, and then perform the actual formal equivalence checking. The designer has access to the original golden netlist as discussed, so he's able to perform this step, unlike the adversary who does not have access. So we have actually created this entire automation by where it follows each of the steps discussed in the previous slide. So as you have seen, when you run the attack, it gives you options, what benchmark you want to use, what attack you want to run. So when you do that, it starts printing out iterations. So each iteration will do all the 4 steps discussed in the previous slide. So first it generates the lock bench, then it tries to run the attack, it extracts the combinational portion of the key, and then it performs formal equivalence checking. So a failure means that it actually returned a functionally correct key. So you're able to see a 0 here, right? So 0 is the functionally correct key, which means you're not able to secure the circuit. So it keeps on running. So iteration 2, again, it generates the lock bench, runs the attack, and checks, extracts the combinational portion of the key, and checks for formal equivalence. Again, it's a failure. Then you have an iteration 3, where again, you do the same thing. Again, it's a failure. But in the 4th iteration, you can see here that the combinational portion is actually not all 0, which means if you apply this key, then the circuit will not function correctly and it is secured well. So once you have a success here, then we actually save the SAT secure circuit in the locked folder. So this is how we do it. So we have seen this figure before. The interesting thing about SeqL is that it is generic. So although we show here the SAT solver, it can be replaced with any other attack, and then you can modify it. So if you see the structure of the SeqL, the way it is organized in this flowchart, it looks like it is only based on Oracle-based attack. But in fact, we can make slight modifications to extend it to other attacks like fall and those kind of Oracle-less attacks. So, but I don't show that here to make it very simple because it becomes too elaborate. But in our paper, we have actually shown the details of all that. So we also try to show an example where we replace the SAT solver using an SMT solver, which means we actually use the API for the SMT attack to replace with the SAT attack. So suppose you run the SMT attack on P1. In the first iteration, it tries to do all that and then it's a failure. And in the second iteration, it happens to be a success. And then we save the SMT secure circuit in the locked bench folder. So in the previous case, what we have seen is that it took 4 iterations actually to return the secure circuit, but in this case, it took only 2 iterations. So it really depends on the search engine. So it happens that SMT is a little faster in searching for the secure circuit. So this is an example of how it scales to other attacks. Now it's important to actually see that it scales well to very large scale industrial circuits. So typically we are trying to actually secure an IP, and we are looking for registers without feedback. And in practice, these kind of registers are practically available for industry scale designs because for testing these designs, there are certain IEEE standards which use these kind of flip-flops in order to isolate them from rest of the design and test it and so on. So those flip-flops can be exploited by locking them and using SeqL and then making them secure. So we have demonstrated the efficacy of SeqL on large-scale designs like ITC benchmarks and also a very practical circuit RISC-V. And the tool flow actually works very fast, even on RISC-V. The entire procedure takes only a few minutes. So we also show an example of RISC-V for showing the efficiency of this attack. So in RISC-V, the first first iteration, when you do a SAT attack, actually is a failure. And in the second cycle is also failure. Third cycle happens to be a success. So, and then we save the circuit. So the beauty is that you have a very large RISC-V processor, but with just 3 bits, you're able to actually secure the design. So it's a very efficient technique. But when the question comes about the brute force attack, somebody actually asked me a question about the brute force attack. So if you have just 3 bits, somebody can launch a brute force attack. So who cares about regular SAT attack, right? So in that case, we need to actually increase the length of the key in order to ensure it is still secure against brute force attack. So the attack still remains the same. You keep locking the flip-flops without feedback. So you take an input parameter gamma, which is a user configurable parameter, which talks about the key length that you're interested, the minimum key length. And then you take a sequential circuit as input, and then other locking schemes, and then you keep on locking, and you produce a locked circuit along with, and then return the key. So you have this thing, and you keep on running the SAT attack and keep on locking until you cross that thing. And if you are within the bounds of gamma, so you have a gamma basically is a user configurable parameter which talks about the area overhead which you do not want to cross from a design point of view. So then after the loop gets completed, it returns a circuit which is secure against the particular attack you're targeting it, and also against brute force attack. So because increasing the key length resists brute force attack, right? So we also show an example for a B1 benchmark that resists the, this is for RISC-V actually. So RISC-V, we have seen earlier that for iteration 3, you have a success itself. So if you run the parameterized flow, then what we see is that the tool actually continues to lock even beyond iteration 3. Earlier, it just quit after iteration 3, right? So here it continues to lock because 3 key bits is very small. So it keeps on going until it is secure. So what are the main conclusions? So we have, so probably I can do a small demo before concluding, but I don't want to switch too many times. So let me conclude and then show the code. So we have proposed SeqL that performs functional isolation and key hiding. The main concept behind which it works is that the probability of functional key decryption is very low when you increase the key length, and the empirical results show 100% resilience to state-of-the-art attacks. Because of the linear increase in the area and exponential increase in security, it is highly scalable to mainstream circuits. And we have also added parameterization to resist brute force attacks. So if you guys are interested in the source code, please contact me. It's also on GitHub as part of the CAD for Assurance website, but it was semi-automated earlier, so I have removed that. It's almost stable right now. It's fully automated, but I'm doing a small fixes. So once it's complete, I'm going to release it there as well. So let me show a small practical demo. So as I've shown in the code, I hope the screen is clearly visible.
Yes, it is.
Yes, okay. So we have SQL Automation here. We need to give the benchmark name and the type of attack you're trying to do. So as we have discussed in the slides, it runs for 4 iterations before it returns a success. So it keeps on locking until it resists the SAT-based attack. And if you see the key that it returns, it is actually a functionally incorrect key. And once it is secure, it actually saves the circuit in a locked folder. So it's also possible to configure a different attack like SMT here. So when you run the SMT, it actually exits in just 2 iterations with a success and also saves the circuit. So this is about B1. I have also talked about parameterized implementation, where it also allows us to give how many flip-flops we are trying to lock or what is the key length. So earlier we have seen for B1 benchmark, SAT-based attack, the flow actually exited after 4 iterations, giving a SAT secure circuit. Suppose if you want to increase the key length and say it is 5, then I think the name is different. So it actually runs beyond the 4th iteration. It also goes into the five iterations. So somebody might ask, why are you using only 5? I'm using only 5 and not beyond because B5 circuit only has 5 flip-flops. So I have also run a flow where I'm trying to lock a RISC-V processor.
Seetal, just a quick comment. Maybe can you, for those who are not for those who don't know the details, can you please show the contents of B01 and the locked circuit?
Okay.
Before we do this other thing. So B01 or these like B02 and other things, these are some well-known benchmarks that come from ISCAS.
So if you want to walk me through the circuit, so these are the regular inputs. And these are the inputs obtained after scan unrolling because you open up the flip-flops. And these are the key bits, SQK key bits used to lock the flip-flop output. And then you have additional FIK key bits used to lock the flip-flop input I mentioned in the presentation. So these are those. And outputs are all encrypted because you're trying to lock the flip-flops. And then if you want to actually look at the key gate, so these are the unrolled XOR chains as discussed before. And this is the output chain, and these are the input chain and output chains. And as we have discussed, we add one extra key gate at the input of flip-flop that will add up to the output chain. So this is how when you lock the circuit and scan unroll, it looks like.
Mm-hmm.
So we have seen about B1 case. So I was also trying to show RISC-V, where I have started the run yesterday night. It has been running for more than 10 hours. And it has completed 19 iterations. So actually, if you look at the RISC-V first iteration, it took only 75 seconds, but it has been running for more than 12 hours and only completed 19 iterations because as the key length increases, the amount of time it takes to actually run the SAT attack also increases. So that is why only 19 iterations have completed. But this essentially shows that I can arbitrarily increase the key length to any size I want to resist brute force attack. So this is where we are. I think the timer shows that my time has completed. I think the house is open for questions.
Thanks, Aydin and Seetal. So we do have 2 questions. You already answered one. There's another question in the Q&A. Can you address that?
Is the locking scheme secure against structural analysis based attacks such as SeeL, snapshot, OML? I think you can use any attack in the loop, as I've mentioned. So we have shown a very broad range of attacks, but obviously we cannot cover all attacks because there are a huge number of attacks. But any attack can be used in the loop, and it will definitely secure because we are doing functional output corruption where some of the keys are hidden and there is functional isolation. So because of the property, it might take more number of keys or less number of keys, more iterations or less iterations. But in essence, whatever be the attacks, SeqL will be able to secure. That's what we try to show in the paper as well.
Okay, there's also another question in the chat window. How long would it take to prevent a 64-bit brute force attack?
Well, it depends on how fast you can run the attack and how much compute resources you have.
Right.
Typically, in the crypto community, people will start feeling safe with 80 bits and beyond. So 2 to the power 64 can still be breakable. So that's why we typically recommend using 80-bit keys or more, so that the attack is not only successful against SAT attacks or SMT attacks or other attacks, but also against brute forcing.
Right. That's the reason I have locked RISC-V with 100 bits because it's more.
So one more thing that I want to mention here. So as Seetal showed, so it may take a while, a few days, to encrypt a large circuit such as a RISC-V, but it's just one locking per design. So once you do it once, then it will be done. So it's a one-time cost.
Right.
Seetal, you mentioned that you will release the code. So that's great. I mean, we always welcome the open sourced tools.
Right.
So also, you may send us the link. So we will update the CAD for Assurance website.
Right.
Yeah.
Okay.
So
okay. Yeah.
Thanks very much for inviting us. And please let us know if you have any issues about running the code or extending the code to your application, running on different attacks, different circuits. We have tried it on many different configurations, but there can always be some bugs. Let us know and we will help you.
That's very helpful. Thank you. Okay.
Thank you very much.
Thanks. Now we have our second speaker, Professor Tamzidul Hoque. He's a professor, assistant professor at the University of Kansas. I think your student, Mahmudul Hasan, will also co-present the work. So to avoid the further delay, so I would give the podium to you.
Thank you very much for the introduction. Let me share my slides. So in the first part, I will give an introduction to our work, and then Mahmudul will share his slides later to go over the demo. Okay. So I hope everyone can see my screen. So in this work, we are basically trying to protect against hardware Trojan attacks in commercial off-the-shelf component. This work is led by me and Mahmudul Hasan at the University of Kansas. We also are collaborating with the University of Florida with Sarup, Jonathan, and Prabuddha. So let me first describe the problem. So we know that commercial off-the-shelf components are very popular means of developing your system. If you think about a custom IC-based system development, what happens is that a system integrator needs to develop an integrated circuit from scratch. So they need to, obtain a design and then fabricate it, do the packaging, and then integrate into their system. So this is a costly process and requires time. So compared to that, if we look at COTS-based system development process, here the system integrator just needs to buy a chip from the market. They do not need to design the IC or or export the fabrication process to someone. They just need to find out the appropriate chip they need into their system, and they just buy it and integrate into their system. So that means that it gives you reduced development time for the system, lower life cycle cost, and then it's easy to integrate new technology as they come in the market because you don't have to design and fabricate it. So that is why COTS-based systems are everywhere, and even in the very security critical domains like military and automotive, you have commercial off-the-shelf components very commonly. Now, let's look at the problem of integrating COTS. So one of the biggest challenge is the trust issue. So when we design an integrated circuit by ourselves, we have some advantages. For example, at least we have the design to analyze for vulnerabilities. Even if we hire a foundry for fabrication, at least when the chip comes back, we can apply a number of different verification techniques. And in fact, a lot of these verification techniques that exist today, they at least need the netlist, whether trusted or untrusted. If you do not have the netlist, you cannot really generate any test vector for verification or do any form of analysis. For custom IC-based system, there are some techniques for detecting hardware Trojan or any type of malicious circuits. But now, if you think about COTS IC, as a consumer, you are buying it from the market, and for you, you do not really have a way to verify the trustworthiness. There could be a hardware Trojan inside that, and you do not have any design or any golden model to perform any type of existing verification technique. So this is a very challenging problem, and right now there is very few solutions that could be applied in this scenario. So let's look at the existing solution and how, why they are not applicable to COTS. So if we just start from the very bottom of this table, if we look at design for security solution, like logic locking, filler cell, these are often proposed for preventing hardware Trojan insertion. But for COTS, you cannot really apply this technique because you do not have any access to the design stage when you are buying COTS, right? These are only applicable if you are designing the IC or you have some access to the design stage. If you want to apply logic testing like Mero or Mars type of technique, you need to apply some test vectors, which are guaranteed to activate hard to activate nets within the design. But if you want to generate such intelligent test pattern for detecting Trojan, you need to have access to the netlist from which this chip was fabricated. So for COTS, you do not have access to the netlist, so you cannot really generate such patterns. Side channel analysis is also a very common technique for Trojan detection, but oftentimes they need access to a golden chip, or they at least need a netlist using which they can generate the test vector to activate any or partially activate any hidden Trojan. So for COTS, side channel analysis is also quite infeasible so far. So so all these post fabrication detection techniques are currently not applicable for COTS. If you just look at the IP Trojan detection in IP techniques like static analysis and formal methods, these are also not applicable because you are dealing with a fabricated chip, not like an IP. And also the IP itself is not available as well. So these techniques are not really applicable. So finally, the two techniques that we can see at the top are possible to apply in COTS. For example, we can potentially apply a hardware redundancy-based technique where instead of using one integrated circuit, we buy integrated circuit from different vendors and say we buy 3 versions of the same chip and integrate into our system like a triple modular redundancy. And at runtime, all the time we compare their output to make sure that if whether there is an activation of hardware Trojan or not. So this is more like a runtime Trojan detection technique, right? Where we need to buy multiple version of the same chip from different vendor. Now the problem with this technique is, first of all, you are only fighting against Trojan that impacts your functionality. As many of the leakage Trojan cannot be addressed. And then another challenge is that you are using COTS for economic purpose. You want to keep your system cost lower. But when you have to buy multiple versions of the same chip, your system cost becomes very high. And the time to market also increases because you have to integrate all these different chips and then test the system. So this is not really attractive for COTS-based system development, the hardware redundancy-based solution. So finally, the solution that I am talking about today is a software-based solution, and this is applicable for COTS because you only need to modify the application software that you will be running on your untrusted microprocessor. Now, that means that this solution is only applicable for COTS microprocessor, okay, not any arbitrary chip. We are talking about microprocessor. And but the challenge for our technique is that you have to endure some runtime overhead for accommodating our solution. But still, this is very attractive compared to the hardware redundancy-based technique, because you do not have to change anything in the hardware to enable a runtime Trojan detection or tolerance. So this is the solution that we are working with. So the solution that we are working with is called a variant-based solution. So imagine that in your processor, you are running a program and it has some input data and it generates some result. And the adversary basically wants to insert a Trojan in the processor that will potentially alter your result when it activates. And by result, I mean some of the variables that are critical and could be, could be attacked by an adversary. So the goal of the adversary is to design a Trojan that will trigger and change your result. Okay. Now, to protect against such a Trojan, what we do is that instead of running the original program, we run two versions of this original program, which we call the variant. And these variants are functionally equivalent version of the original program, but structurally within the code, they are very different from each other. So you can see that we are first running the variant 1, and then we are running the variant 2, and they are generating some results. And then we are comparing this result. Now, if there is no activation of hardware Trojan in the field, then we can expect that these variants will generate the same output because they're functionally equivalent. And if they do not generate the same result, then we can assume that there must be something wrong. Maybe there was a Trojan activation and the Trojan has impacted one of the execution of the variants, right? So in this way, we can actually detect activation of certain hardware Trojan that is impacting your functionality. We are not really dealing with a leakage Trojan. And in fact, by running more variants, you can actually tolerate the activation of the Trojan, not just detect it. So once we see that the results are not equal for these two variants, we can run more variants like variant 3. So by running 4, 3, 5, 7 variants, we can compare all the results and do a majority voting to even to find the correct output and basically tolerate the impact of the Trojan. So let me give you an example of how that would help us to fight against Trojan. So let us assume that we have a Trojan, a sequential Trojan in a processor, and this Trojan has 4 states, S0, S1, S2, and then finally it triggers. So this Trojan will only get activated when specific input patterns are received, which basically helps the Trojan to reach the final trigger state. Now, this Trojan is basically taking the trigger signal from various internal nets of the processor. So as soon as the specific values appear on those nets, the Trojan changes its state and it reaches the trigger condition. So you can see that there are the path that it can take to trigger is basically will require it to have these specific hex values that are shown in the state machine. So let's say that we run the first variant, and what it does is that it just has the right, it produces the right internal activity to trigger the Trojan. So you can see that the state machine moved from S0 to S1 to S2 to finally it triggered, and it impacted, say, one of the variables of the program. Now, if you run a second variant, which is structurally very different in terms of its code, the internal activity of the processor will become very different. And that is why when the variant 2 executed, the same Trojan did not activate. It only moved from state S1 to S2, and it did not reach the trigger state. So you can assume that the output or the variable that got impacted in variant 1 execution did not have the same impact on variant 2. Most likely the variable's value is correct when the variant 2 is executing. So now if you compare, as I showed in the previous slide, we will be able to see that variant 1 and variant 2 did not produce the same output. And at this point, we can run variant 3, which is also different from the first two variant. And now it also does not trigger the same Trojan. So variant 2 and 3 produce the correct output, while variant 1 produced the wrong output. So we can detect the Trojan as well as we can identify the correct value of the variable that was impacted. So this is the fundamental idea on how the solution works. And our goal is to generate variants that are drastically different from each other and can produce significantly different activity inside the processor when they execute. So to understand that, we actually generated variants for a processor, and this is just an example result from a program. So we actually analyzed all the internal nets of a processor, and when we were running the first variant, we considered different rare nets. And observe that if those rare nets were used for designing a Trojan, how many of them would have triggered? So we can see that for variant 1, there are approximately 963 Trojan, 4-input Trojan that are possible to design. And then we also looked at the same trigger conditions when we ran the variant 2. And we observed that only 74 of them again achieve the same trigger condition. So that means that if there was a Trojan in that trigger condition, only a few of them would have re-triggered. And unless a Trojan re-triggers in multiple variants, it is likely to produce a correct output. So we just repeated this experiment for larger Trojan inputs. So for 8 input, it means that it's harder to activate Trojan. And as we increase the activation difficulty, we saw that the rate of re-triggering reduces drastically. That means that our solution is very strong against Trojan that are hard to activate. And those type of Trojan doesn't re-trigger in multiple variants. So those Trojans are likely to get detected if they ever activate. And also it is easier to tolerate. So this is a high-level idea of our solution. Now we have developed a tool which can automatically generate these variants and can integrate into one executable. So if you give a program to the tool, it can actually generate many different variants. And from those large number of variants, it selects the most diverse variant. And once the most diverse variants are selected, those are integrated into one executable, as shown in this figure. So from here, my student Mahmudul Hasan will share his screen and give a demo of the tool.
So I will present the tool demo what we developed so far. So our chosen resilience computing trick is a novel approach that can detect and tolerate the activation of hardware Trojans in untrusted COTS component, right? And through the modification in the application software running into. So our tool, this is achieved by executing multiple functionally equivalent software variants instead of the original program and comparing the results. Therefore, our trick doesn't rely on any hardware redundancy or the architectural modification. So to automate this process, we developed a software tool that is Trick. So our Trick tool has been designed to generate program variants automatically, then find out the best variants using a metric, and finally integrating the additional code for calling the variants and comparing the variants output of variables, and finally compile all the variants in a single executable file. The complete process is presented in this workflow. So our Trick workflow can be divided into 3 major stages. So you can see here that is workflow 1, 2, and 3. So in the first stage, we are passing the source code in a pre-processing stage. So the pre-processing stage basically adding some additional codes for storing a specific register or variable's value in a separate text file for each variant that a user doesn't want to see affected by the Trojan application. Therefore, the provided source code is passed through a compiler to generate an intermediate representation file, and onto that IR file, we are passing different optimization techniques, and we are finally generating those unique assembly variants that are functionally equivalent but structurally different. In the second stage, we are analyzing the diversity among the variants by analyzing their opcodes and operand, and finally calculate the similarity of each pair of variants. From the information, we select the number of set of variants for user wants to run. Let's say if a user wants to run 3 variants, so we'll create the symmetry score of 3 set of variants. From that information, we select the 3 most diverse variants, and in the correct methodology, 2 variants are always executed at the runtime. The third variant is only performed when the output of the variable of 2 variants doesn't match, and the majority voting might be required. By choosing the 3 most diverse variants, we ensure that the Trojan has a minuscule probability of getting triggered in 2 or more variants. So if the same, the Trojan activates in more than 1 variant, it could potentially bypass your comparison. And finally, the integration of a top program that is in workflow part 3. So now I will go through the briefly in each of the workflow, right? So we use the LLVM compiler infrastructure for our workflow part 1. So the LLVM is a collection of a modular and the reusable compiler and toolchain technologies. Therefore, we are passing our source code, if there is multiple, into the plan, and we can generate a multiple intermediate representation file, and we can merge them into a single intermediate representation file. And finally, we can pass a database of optimization sequence onto that intermediate representation. So the intermediate representation is basically the encoding of a program, and the intermediate representation is basically a breakdown of the source language and constructs over several small steps to the target assembly, the target code that is that can be x64 or the RISC or the bits any processor. So finally, from the different level stages of intermediate representation, we are generating the unique assembly variants, and also from this unique assembly variants, we are generating the executable files. So at the end, in workflow part 2, we will pass this ASM list to analyze the diversity among the cores and find the least similar variants and use those executables to finally integrate the top module. So if you want to see one of the database, the pass sequence, you can see here, we're using different pass sequences supported by the LLVM compiler. So here, this is a snippet of the diversity between 2 variants. So in you can see here there are 2 program variants in the assembly level, and it has different the tool flow, the configuration path flow, and you can see here there is significantly difference of using the different registers, different opcodes, and the path program path basically. So now let's get back to the workflow part 2. So to calculate the similarity score, how the programs are diverse from each other, we follow a method called that is opcode graph similarity. So this is a technique is used for finding the similarity score of assembly files based on the opcode graphs or countables. So in this technique, first a table is created by extracting opcodes and the operands from the source assembly code using a Python script. You can see the table here in the 5 column here, that is ASM opcode countable. So what basically we are doing here, for example, we are taking 2 assembly variants and we are storing the frequency of each opcodes here. So let's say you can see here in the row 2 and the column 3, this sub opcode is following the move opcode twice here. You can see in the line 2, 3, and 5, 6. So that's why the value is 2 here. And so same table has been created for the another variant. And finally, from this frequency of opcodes, we are generating another table that is basically give us the similarity of these two variants. Let's say for this first variant, you can see here the value of sub is following the move is twice, and also in the second variant, the sub is followed by the move twice. So that's why the value is 0 here. And in case of the other, that is this move is followed by the push opcode, the value is 2. And here the move is followed by the push is 1. So we are taking the value only 1 here, because there is only one similar frequency of that opcode into this two variant. So we are taking the least one, and from that table, we are generating the similarity score. So you can see here in the third row, I mean, this program 1 and program 4 have the least similarity score. That means the frequency of opcodes are not common into this program 1 and 4 assembly. So we created the same table for this operand, and finally generated the similarity score using this opcode and operand frequency table. So if the user wants to run more than 2 variants, then he or she can generate the 3 variants table using this the pair of variants similarity score. Finally, in the workflow part 3, that is the integration. So when the untrusted COTS cursor operates in the field, we envision that the first and second variant will execute and store their variables output separately. Then those output will be read back and compared. Suppose the output of a variant changes due to the execution of the frozen circuit. In that case, the comparison result will raise a flag, which will initiate the execution of the third variant, right? So after that, a comparison will take place among the outputs of all the 3 variants in this space. And if necessary, we'll do the measure reporting, and we can also compare the variables result if we have the golden data for the variables of the asset and find the correct output. Therefore, we need some additional codes for their execution and comparison results. That's why we are calling this workflow part 3 as integration. So we are integrating the variants that are selected in the previous workflow 2. To automatically combine the variants and include the required codes for this task, the take tool reads the generated variants and create a new C program that is we're calling this top program, and calls this variants and finally comparing the results. Finally, the take tool compiles these variants integrated code and generates executable for the target architecture. So now I will go to my Windows, the Linux machine to give you the demo. So so this is for our tool flow. We are using LLVM and Clang version 10 compiler, and we use Python script, and this is the library we use, and the operating system was used higher than 18.4. So this is our directory structure. You can see. So for first the pre-process, we use this variable insertion Python script and the configuration text file. So for the task, we take an encryption program that is P32.c. So you can see here, this is encryption program, have encrypt and decrypt function and the begin function. So this take to this number and finally encrypt and decrypt this two number. So let's say a user want to insert or observe the variable, let's say this delta, and the encryption output, that is this D. So in this variable check config text file, what we are basically doing, we are putting the variable names we want to protect and the line number from where we want to add the additional codes for printing the variable's output in a text file. So after adding this information in the configuration text file, so now we will run our variable insert Python script to generate a new C program that is preprocessed. So let's say our program, in that case, that is this T32.c. So if we run this script, so we can see the variable inserted successfully. So if we want to see the difference between this two program, that is the T32.c and the newly generated variable inserted T32.c. So you can see here in this program, this new program, some additional code has been added for storing the variables output in different file names during the runtime execution. So also the command has been added to printing out the variables into the output file. So after that, we have this run of script. So that basically apply the optimization passes, which the passes are, the optimization is stored in this text file. And this text file has been used to generate the unique variance. So to run that script, we will use run opt.exe, and we'll give a program name that is, let's say, T32, and the newly generated C file. After running this script, we'll observe that a directory structure has been created that stores the different level of intermediate representation files of our program. So after passing different optimization techniques, we created this number of unique assembly files that are functionally equivalent but structurally different. And some of the assembly files have same, the exact same architecture. That's why we are only keeping the unique variant, only the unique ones. So you can see here we generated the unique assembly variants and also the executables. So after that, we'll analyze this set of assembly files to analyze the output and operands and generate the most diverse variants. To do that, we'll run our Python script. Our program name is T32, and let's say we want to generate the 3 variant. So if we put that, so you will see after running this Python script, so that this tool will give us the most unique 3 variants. So let's say we want to see the difference of these variants. So you can see here, these 2 variants, they are functionally equivalent, but significantly different in the using of the control flow, also the opcodes, and the using of the registers. So that assures that the internal flow, signal flow of running this variance in the COTS component will be different, right? So there's the difference between these 2 assembly cores. And finally, after running this Python script, you can see here we got the simulated details, the simulated score. If you want to check that, the simulated scores, you can see here we almost generated each pair of simulated score of the variance, right? So these are the scores are different. And from that, we generated the variant of more than 3, that is this 3 set of variants that we will run and we will use in our main program. So you can see here the different scores here. Finally, also this top program has been generated, and to make it executable, we will run run top exe program, and we will give this this CPP file to this, and we will see a newly directory will be created, that is take files output. So in this directory, we finally generate the executable of our top program, and if we run this, we can see here the program ran twice, and the original value was this, And after encrypted the value, we got this, and the decrypted, we got these values. And this is saying that variant 1 and 2 is equal, because if you see after running this executable, this 2 output file has been created. So basically this output file is storing the asset or the registers or the variables value that is obtained at the pre-processing stage, right? So if we want to open this 2 file, so you can see here this output files are basically storing the variables value. So this 2 is basically the, the main functions, encryption or decryption variables, and this one is the delta that is, that is in the another function that is that was decrypted. So here, this is the delta one, and the final, the B that is we are using to encrypt and decrypt. So I hope you got my to helpful and understand the workflow. So yeah, so let me share my slide again. So yeah, thank you. So if you have any question, please ask us.
Thanks. So let's see if we, for some reason, we have a question from Xiaolong. Xiaolong, can you type in a question in the Q&A?
I can see the question in the
Oh,
chat.
okay, that's great.
So the first question is that, is the Trojan trigger conditions are pre-known? So no, the Trojan trigger conditions are not pre-known, and but what we try to do is that we try to generate the variance such that if there is a Trojan if there is a trigger condition, then it will not reappear in the other variant. So we try to make the variance such that if a Trojan gets activated in one variant, it doesn't get activated in another. So, and we do that by generating the diverse possible version of the programs. But we do not assume that we know any Trojan condition. Another thing that we observed was that if the Trojan condition is extremely hard to activate, it actually never activates in multiple variants. And that is intuitive, because a program that activates that hard to activate condition, another program which is completely different from it will not reactivate it. So that actually works in our way, because we actually assume that an attacker will try to design a Trojan utilizing the rare activation condition, and if the attacker doesn't use the rare conditions, it is likely to get activated in a regular pre-verification process. So the second question is, what if the Trojan is hidden in the IP inside the system on chip rather than in the CPU? If the Trojan is not triggered by the CPU instruction inputs. Yes, so we assume that the Trojan is inside the CPU, not like any other IP in the SoC. And if it is outside the CPU, then it will most likely get bypassed, because the CPU will get the same corrupted input from the other IPs. So it is unlikely to be able to resolve that Trojan. But if the Trojan is inside the CPU, then we can assume that it should be able to detect any anomaly caused by the Trojan. Please let me know if that answers the question. Thank you.
Thanks. So I have a general question. Is your tool be released already, or do you plan to do that? Because in our CAD for Assurance website, it seems that we don't have a link for your tools. So I don't know whether it's our mistake or it's something you have not released yet.
So we have not released it yet because it is still a work in progress. So once we make it a bit more mature, then we will definitely consider sharing the tool. Yeah.
Okay. Okay.
Yeah, first of all, thanks to all the speakers for giving an excellent presentation and demo of their CAD for Assurance tools. This is definitely very, very helpful for the entire hardware security community. So really appreciate your contributions, and would like to also acknowledge the support from the IEEE CEDA team. Dana is here, and Amanda and others in IEEE CEDA support team. They have done an excellent job through these series of webinars and panels. So I really appreciate the support, high quality support we have received from them. Thanks very much on behalf of the organizers. I also do like to thank all the participants in the audience. Without you, of course, there's no point of doing these things. So I really appreciate the constant support and help we have received from all of you in these webinars. We see a constant interest in this. Of course, hardware security community is a rather small community, very well-knit community, but rather small compared to maybe other communities like AI community. But it's a growing community. It's an important community, and we are happy to serve to the community and serve the community by organizing these webinars and also by sharing the information about the tools in the CAD for Assurance website. The final comment I would like to make here is that this particular website, that's cadforassurance.org, as well as these webinars which we are organizing regularly, it includes the panels. There are 3 panels already held. All the panels are extremely well received, and you can actually watch the videos for these events in the CEDA website if you have missed some of them. But these events are organized with the help from the entire community. So as you can see here, large number of people have come forward to enable organizing these events. What we would like to do here is to solicit your help, your participation in organizing these events, in uploading and sharing your tools, so that we can move ahead with this effort in 2022 as well as in years following that. So if you have any CAD tool which relates to hardware assurance, if you have any benchmarks, if you have any metrics, if you have any significant publications, please do share that. There is a form in the website. If you go to cadforassurance.org, there is a form in the website which will allow you to, even though it says upload your tool, but if you have benchmarks or any other things, you can simply use the same form and upload the information, and we'll be able to put that into the website and acknowledge your contributions. So that's something you can do. And also, if you're interested to do an webinar of your tools, so let Dr. Jean or me know, or any of the organizers know about that. You can email us. You can also probably find our phone numbers in the web. You can also call us. So with that, I would thank all of you one more time, and we'll look forward to seeing you in the next events. If you go to the website, CAD for Assurance website in CEDA or also in the cadforassurance.org website, you will see the details on the next few events. We have already planned for 2 other webinars in 2022. So we will look forward to having you in those.